Alright guys, welcome back to another lecture. This is the second part of our linear independence and dependence lecture. Prerequisites, as usual, are here on the board. Make sure that you've watched part one, because of course it's not going to make a lot of sense without part one. And we're also going to need to be able to take determinants. Okay. Now I'll give you a quick sort of recap for what part one gave you. Part one gave you the concept behind what linear independence and dependence was for any sort of collection of vectors in a vector space. It also gave you a process by which we could take vectors within a real vector space, Rn, and determine whether or not those were independent or dependent by putting them into row echelon form. Right? What we could do is we could take the number of vectors, say we have 7 vectors, you put them into your matrix, you find the row echelon form, and if the rank of that matrix turns out to be less than the number of vectors, then it's dependent, right? Because the rank sort of represents the amount of information relative to the actual set itself. So let's discuss how we might use determinants to shortcut that process a little bit. Okay. Now, the very last example I did in part one was the following. I took these 3 vectors, I believe. Yeah, well, okay, I think of these vectors. And then what I did was I put them into the columns of a matrix and then put it in row echelon form. Do I have to use the columns? No, you could put these into rows. Either way works. It turns out that there's an equivalence between the rank of the column space and the row space of a matrix, but we'll get to that in another section. Okay. What we did was we took these vectors. Let's put them into our columns, 1, 2, 3, 4, 5, and 6, 7, 8, and 9. We did some elementary row operations, which gave us the following: 1, 4, 7, 0, 1, 2, 0, 0, 0. And what we saw was that this collection has rank 2. Okay? This collection has rank 2. There are 3 of them. Okay? So in this particular case, we have the number of vectors, n. Okay, that's 3. Whereas the rank is 2. And since the rank is less than the number of vectors, we know that this is linearly dependent. And again, of course, we know these things because these are vectors in 3 dimensions. And all 3 of these vectors lie on the same plane. I don't need 3 vectors to describe a plane. 2 is plenty. So, how might we do this? Well, when we're talking about linear dependence and independence, as long as we're talking about real valued vectors, we can boil it down to the definition of dependence or independence, or the value, I should say, for the independence or dependence of this set is equivalent to the value of independence or dependence for any matrix which is row equivalent to it. Okay? So again, if I perform some elementary row operations here on this matrix, whatever matrix I get out, if this is dependent, the original was dependent. If this is independent, the original was independent. Right? Now, really then what I'm looking for is, well, let's think about what it means for the rank to be less than the number of less than the number of vectors. Wouldn't I have to have at least one all 0 row? Right? I mean, if this row wasn't all zeros, then it would have rank 3. And of course there are 3 vectors. It's only by virtue of the fact that I have a row of all zeros that this matrix is in fact, well, constitutes a collection of dependent vectors. So how might I leverage this knowledge to bring determinants into this? Well, what we can do is we can observe the fact that elementary row operations performed on a matrix alter the value of the determinant in very specific ways. Okay, and again, this is directly from the determinant video. If you haven't watched it, again, make sure you watch it. But I'll give a quick recap here. Okay, so what I know that if you permute, okay, permuting causes a -1 scalar value to accumulate here, right? But notice that again, it's just a scalar multiplier, okay? So if I'm doing several row operations in the process of taking a determinant, I might get several -1s all trapped on the outside, okay? The multiply operation, okay? The correction for this, whenever we're trying to take a determinant, is to take a reciprocal scalar coefficient as a correction on the outside of my determinant. And we remember that the add function, this was the nice one, well, the add function does nothing, okay? Okay, so what does this mean? This means that hypothetically speaking, let's say you take a matrix A. I want to take, so here's A. Okay? And I'd like to take the determinant of A, but what I'm going to do is I'm going to perform several elementary row operations. A lot of them. Right? Okay, just a whole bunch of elementary row operations. And at the end, I've got a new matrix B, which is in a much nicer form. What will I have accumulated on the outside of this? Okay, well, it's got to be just a collection of these scalar coefficients, right? Yeah? And so I can rewrite this in sort of a more natural form, right? I can rewrite this whole thing as, okay, suppose B is a row echelon form of A, right? So I know that I can accumulate, that I can get to B from A via a series of elementary row operations, okay? Then here's what I know. Then the determinant of A is equal to -1 to some power. Well, I'll use a random variable here. We'll say to the x power, okay? Where x is the number of permutations that I had to do to go from A to B, okay? Times a product of scalars. We'll call them K1, K2, all the way up to Kn. Well, n's a bad choice. Sorry. We'll say K. Linear algebra uses so many letters. I don't want to use I or J or N. I don't want to use Y. We'll say Z. Why not? There we go. Okay. So a whole bunch, and that's for every single time I had to use the multiply operation. Right? Every time I use the multiply operation, I'll accumulate another scalar on the outside, and then finally, this will be times the determinant of matrix B. I don't have to account for any of my adding operations because of course those have no effect on my determinant. Okay? Now, here's the interesting part. We'll tie all these things together. In order for a collection to be dependent, then the collection of real valued vectors in matrix form would have to have a row of all zeros. But every matrix with a row of all zeros, doesn't it have a determinant of 0? Right? Because I can reduce a determinant of a matrix of this form by any row or column I wish, and if I choose the bottom row in this case, then I'm going to get 0 times a cofactor plus 0 times a cofactor plus 0 times a cofactor. That all those things are 0. But understand what that means. That means if A is row equivalent to a matrix that has at least one row of all zeros, then the determinant of A would have to be this times the determinant of B, but the determinant of B is 0 since it has a row of all zeros, which implies, of course, the determinant of A is 0. And that is a fantastic result, right? What it means, and I'll go ahead and put the theorem up here in plain English. What it means is that we know that for a collection of n, for a collection of n real valued vectors, which are a subset of Rn, then the collection, I'm not going to rewrite it, I'm just going to put it here. The collection is linearly dependent if and only if the determinant of the matrix with column vectors v1 to vn so this would be an n by n matrix if the determinant is equal to 0. This gives me a quicker way, computationally speaking, to figure out whether or not a collection of vectors is linearly independent or dependent. Now this is not, I say this is a wonderful result, and it is, because we're of what we're going to use it for next, not necessarily what we're using it for now. There are some drawbacks here, right? For example, suppose you were asked if the following collection is linearly independent or dependent. Well, that doesn't work anymore, right? Why? Well, the problem is I can't make a square matrix out of these, right? These vectors are elements of R4, and of course I only have 3 of them. Are they independent or are they dependent? Well, I can't use this theorem for it. I'm going to have to put these into a matrix. I'm going to have to put it in row echelon form. I'm going to have to determine the rank. Okay, all those things. And remember, that always works. For real valued vectors, putting them into a matrix, putting it in row echelon form, looking at the rank, comparing it to the number of vectors you started with, it always works. Okay, but we could do a determinant as well. Okay, now we did just work an example where that might have worked. Okay, let's look at the determinant of 1, 2, 3, 4, 5, 6. And we've done this determinant before, so okay. If I look at the determinant of this, sure enough, I get 0. Okay? And again, taking a determinant of these and you get 0, all that means is that it has a row echelon form that has a row of all zeros. Okay? Now, in our case, that implies dependence. Now, honestly, which one is easier? For you guys, if you're dealing with real valued vectors, it's going to be easier for you just to put them in a matrix and put a row echelon form. Taking a determinant, the classic way, the cofactor expansion way, is of course a non-polynomial time process. So yeah, we don't want to do that, right? If you use the row operations to reduce the determinant, well, fine, but if you're going to do that, I mean, if you're going to do in the row operations anyway, why not just, put it in row echelon form? Why do I want to bring something like this up? Because again, and I mentioned this at the end of the previous video, what we really care about is how do you determine whether or not functions are linearly independent? For example, f1 is sine of x and f2 is cosine of x. Okay? Now both of these are members of C infinity. Okay? So we know that f1 and f2, these are both elements of C infinity. These are infinitely smoothly differentiable. And C infinity is, of course, a vector space. But are these things linearly independent? Well, how do we figure that out? Well, I could try the long way. I could say, okay, let's look at C1 times F1 plus C2 times F2, and if that equals 0 vector, it's linearly independent if these two things must be 0. Okay, so I've got C1 times sine of x plus C2 times cosine of x equals 0. How do I know? How do I know they have to be 0? I have no way to solve this, okay? There's just not enough information here to do it. Well, the question of how to determine whether or not these things were linearly independent or dependent was eventually solved by a mathematician by the name of Wronskian, okay? And he devised an interesting test for independence, not for dependence. Okay? Let me explain what that means. First, we have to build the Wronskian. I'm going to build a matrix, and I'm going to build a square matrix so that I can take a determinant afterwards. Now, first of all, I'm looking at the number of vectors I have. I've got two vectors, which means I'm going to want a 2 by 2 matrix. And it makes sense for the matrix I'm building just to go ahead and use the values I have as your A11 entry and your A12 entry. I mean, if it's going to be a 2 by 2 matrix, I mean, make that row 1. Now, unfortunately, you'll notice I'm missing a couple values. If it's going to be 2 by 2, well, you know, I need 2 more values. To make the Wronskian, here's how you fill out the remaining rows. What you're going to do is you're going to take a determinant of a row to make the next row, okay? So to make the second row, I'll take a determinant of the first. A derivative of the first, I'm so sorry, okay? All right, the derivative of sine x is, of course, cosine x, and the derivative of cosine is negative sine x. And there's my matrix. If I had 3 of these, I would take the first derivative and then the second derivative. If I had 4 of them, I would take the first, the second, and the third derivative. I take as many derivatives as is necessary to make a square matrix. And then I just take a determinant. Okay? Okay, well, it's 2 by 2. This is pretty easy. So I've got negative sine squared x minus that product. So minus cosine squared x. This is negative 1 times sine squared x plus cosine squared x. This is 1. So this determinant is just negative 1. Now, there are 2 possibilities when we take a determinant here. 1, the determinant might come out to be identically 0. What do I mean when I say identically 0? I mean exactly the number 0. Okay? I do not mean the determinant came out to x and that might be 0. No. X is not the number 0, right? So again, it either comes out to specifically the number 0 or not. Okay. If it comes out to anything other than 0, then it's linearly independent. So, just by virtue of the fact that I took a determinant here, this is my Wronskian, and I got a number that's not 0, okay, so I can say since negative 1 is not 0, the collection sine x and cosine x is linearly independent. Okay? That's it. We're done. That's really nice, right? Yeah? In fact, it seems pretty easy. Seems, you know, a little bit maybe too good to be true. Like there's maybe some weird exceptions. Yeah, all right. So what's the problem? Okay, the problem is I said that if the determinant comes out to be non-zero, something not identically 0, then it's linearly independent. The problem is the converse of that statement is not true. That means if this came out to be 0, that doesn't necessarily mean that it's linearly dependent, not for functions. Now you might be asking, well, yeah, but didn't you just give me a theorem that said that if I took a determinant of a matrix and came out to be 0, then it was dependent? Yes, but that was for real valued vectors. You might notice taking derivatives here, that's somewhat arbitrary, isn't it? Like I wasn't given these functions, I was given these functions. And unfortunately, that amount of play, that amount of error that's built in by taking these determinants, which are not exactly the functions we're working with, unfortunately can build in some wiggle room with the determinant itself. Okay, so again, with the Wronskian, okay, determinant's not 0 right here, then it's linearly independent, guaranteed. If it is 0, we have some more work to do, and I'm going to do a couple examples so that we can see what that looks like. Okay, so first things first. Let's do an example where it comes out linearly dependent. Okay, so let's take a collection of functions. I'll take 2. F2 is 5 minus x squared, and F3 is negative 7x squared. And I know that all of these things, all of these are members of P2, right? My vector space P2. Okay, let's use our Wronskian to see whether or not these things have a determinant, or at least a Wronskian value of 0. So I'll go ahead and put them into my matrix. I've got 2, 5 minus x squared, negative 7x squared. There are 3 of these, so I'm going to want a 3 by 3 Wronskian. I'll take a derivative here. I've got 0, negative 2x, negative 14x. And one more derivative to make another row, 0, negative 2, negative 14. Okay, fantastic. Okay, now, take a determinant. I'm going to expand this using cofactor expansion. Do I use elementary row operations? You can, but honestly, a lot of the times these things will become worse, not better, if you make some poor choices on which elementary row operations to do. We're a bit lucky here because column 2 is perfect. It already has multiple zeros in it, so I'm going to expand by column 1. All right, so I've got 2 times negative 1, that's the 1, 1 entry, so that's 1 plus 1, so that's the second power, times the cofactor, times the minor here. All right, so I've got negative 2x, negative 14x, negative 2 and negative 14. Okay, and I could keep expanding this, but notice that the matrix entry for A21 and A31, those are both zeros, right? So I'm going to get 0 times the cofactor for 2,1 plus 0 times the cofactor for 3,1, and the values of all those things are 0. So let's look at what we have here. Okay, so I've got 2 times negative 1 squared, that's just 2. Okay, 2x times negative 14 is 28x minus negative 2 times negative 14x, that's 28x. Yeah, this is 0, right? Okay, so we took a determinant and it came out to exactly the number 0, identically 0. Does that mean that this collection of vectors is linearly dependent? No. Okay, we cannot use the Wronskian that way. To demonstrate dependence, we're going to have to actually find a dependency relation. Okay, so once I do the Wronskian, once it comes out to 0, I think to myself, oh, all right, now I got to do some more work. How are we going to demonstrate a dependency relation? Well, we're going to go back to the definition, right? So now that I have this, I'm going to go back to the basic definition. It didn't work. I took a gamble. Maybe it was going to be non-zero, right? So I go back to my original definition, and that is C1 times my first vector plus C2 times my second vector plus C3 times my third vector are equal to the 0 vector for my vector space P2. That's 0 plus 0x plus 0x squared. And my question is, what are the solutions possible for C1, C2, C3, which will hold this equation? Let me distribute and I'll collect all of my coefficients. What I get here is I get, as my constant term, 2C1 plus 5C2. And as my x squared term, I get negative C2 minus 7C3 x squared. All right, so remember, the left-hand side and the right-hand side have to have the same coefficients. So here my constant coefficient on the left is equal to my constant coefficient on the right. That gives me 2C1 plus 5C2 is equal to 0. Same thing is true for my quadratic coefficient, which tells me negative C2 minus 7C3 is equal to 0. Solving here for C1 will give me C1 is equal to negative 5 halves C2. Solving here for C3 gives me C3 is equal to negative 1/7. I wrote C1 here. C3 is equal to negative 1/7 C2. Okay. So any coefficients that satisfy these two conditions will, of course, result in a true equation here. So pick something. I choose C2 is equal to 14. Okay, because it's going to make some nice whole numbers. So it doesn't matter what you pick. You can pick C2 is equal to 1 and leave the fractions. It's fine, right? So if I pick C2 is equal to 14, notice that implies that C1 is equal to negative 35. Okay, it implies that C3 is equal to negative 2. Okay, so apparently 35, 14, and negative 2. This is a non-zero, so not all zero collection of coefficients, which causes this linear combination to equal 0. Therefore, this is linearly dependent. Because remember, independent means that the only solution here would be all zeros, and we found a solution which is not all zeros. Okay. This seems reasonable. Now you may have noticed something. It seemed like we wasted a lot of work, right? Yeah, we did a Wronskian. It came out to be 0, but then we had to go back to the basic definition anyway. What was the point of doing the Wronskian if we thought it was going to be dependent? Well, again, it's a bit of a gamble, right? You're going to have to sort of make a guess. If you think that it's going to be dependent, then maybe try the base definition first, right? Yeah? If you think it's going to be dependent, then you can't use the Wronskian to prove that. The Wronskian only can demonstrate linear independence among vectors, not dependence. Okay, let me show you one more example, one last example. I'd like to show you an example where the Wronskian comes out to be 0, but the collection of vectors comes out to be independent instead. Because to be fair, when that Wronskian came out to be 0, we all kind of thought it was going to be dependent anyway, right? Okay, so let's do the following. Let's make okay. So F1. You know, I'm going to pull this example out of your book just to make sure that I don't accidentally pick something that's, you know, not going to work very well. So let's go with F1 is equal to x squared. Okay, and F2 is equal to the piecewise function. 2x squared and negative x squared. It's going to be 2x squared if x is less than or equal to 0. It's going to be x squared if x is greater than 0. Okay. Now, these two functions are both members of C infinity. Okay. Well, so they're both members of C1. Okay. regardless, they're both members of a vector space, right? They're both members of C1. Okay, because they both have continuous derivatives. Well, they'd be members of C0 anyway, so whatever. Anyway, let's go ahead and make our Wronskian. Now, the problem with making a Wronskian here is I've got two functions. I'm going to need to take I'm going to need to take a derivative here. But the derivative of a piecewise function is conditional. It's conditional on the values. So I'm going to need to do a couple cases. Okay, so let me go ahead and do case 1. Okay, and case 1 will be where x is less than or equal to 0. Now in this case, my Wronskian is going to be x squared and 2x squared, because of course these are the two values of my function when x is less than or equal to 0. Okay, going ahead and taking my derivative, I get 2x here, I get 4x here. A very easy determinant gives me 4x cubed minus 4x cubed, that's equal to 0. So I'm halfway there, right? What about the other one? I mean, if the other one's not 0, then it's got to be linearly independent, right? Well, let's look at case 2. Okay. Case 2, clearly that's the other case, so that's where x is greater than 0. Okay. And again here, my functions change a bit. First function is still x squared, but my other function is negative x squared. Again, the value for f2 once I'm larger than 0. Taking my derivatives just to fill out this Wronskian, I get 2x and negative 2x. Again, take a determinant. We get negative 2x cubed plus 2x cubed also equal to 0. So note that again, no matter what my value for x, my Wronskian comes out to be identically 0. So what do I need to do? I need to check for the actual definition. So let's do one at a time. We've got case 1, we've got case 2. Let's go back to the original definition. The original definition says C1 times my first function plus C2 times my second function. We need this to equal my 0 vector, in this particular case, 0x squared. Collecting these things, we see that we've got C1 plus 2C2 x squared equals 0x squared. And so, of course, we just get C1 plus 2C2 is equal to 0, so C1 must equal negative 2C2. And again, any two coefficients which satisfy this condition will work. Okay? So this is leaning towards dependence, isn't it? But let's do it over here as well. Okay? Again, applying the same rule, the basic definition for linear independence, we've got C1 times x squared plus C2 times negative x squared. That's equal to 0x squared. Collect all my coefficients. I've got C1 minus C2, x squared equals 0x squared. C1 minus C2 equals 0, so C1 must equal C2. And again, any pair of coefficients satisfying that condition will of course work. What's the problem? In order for this to be linearly dependent, I would need a set of coefficients which satisfy both rules at the same time. Well, that's not going to work, right? Because in order for both of these things to be satisfied at the same time, what you're telling me is, you're telling me that C1 is got to be equal to negative 2C2, while at the same time, C1 must equal C2. Well, combining these two equations by substitution, we've got C1 must equal negative 2C1 by substituting in C1 is equal to C2, which gives me, of course, 0 is equal to negative 3C1, which implies C1 must be 0. And of course, by that equation, C2 must be 0. So what our work has shown us is that in this particular case, despite the fact that our Wronskian has come out to be identically 0 for every possible domain value here, we get a set of conditions for the coefficients of the linear combination which force the coefficients to all be 0, right? This definition for your linear combination for the 0 vector only functions if every single one of your coefficients is 0. Okay? That's fantastic, right? So this is an example of Go ahead and write it up here. Linear independence. This is linearly independent. Again, by the original basic definition of independence, namely that in order for this to be true, C1 times F1 plus C2 times F2, both C1 and C2 must be 0. Okay? All right, guys, as normal, make sure you take care of all of your homework, work through these. There are some examples like this already listed in your homework on the Canvas page. If you have questions, email me. I'll see you guys later.